We are continuing to look at valence bond theory. This is the example we worked last time. It was a generic example of an octahedral electronic geometry, which you can see here. In particular, this referred to anything that's silicon through argon. So that's the third period, those that can have an expanded octet and have low-lying d orbitals, as you can see. Here's a real example, or a specific example, SF4. If you draw the Lewis structure for SF4, you should come up with this. You should know it's an octahedral, and you have, of course, 6 bonds here. So you have 6 sigma bonds. 1, 2, 3, 4, 5, 6 sigma bonds, right? And that's the hybridization is sp3d2 as shown here. And each of these has a single valence electron, and so, or a single electron. They happen to be also valence electrons, but sulfur has 6 in itself. And you also have to take into consideration the formal charge of your central atom, and here it is 6 minus half of 12, of course. So that's 0, which means we do have the 6 electrons that go in there. And I'll give you an example later on where you have to pay attention to the charge and you subtract or add an electron, right? So if you had a formal charge of -1, you would add an electron to that. If you had a formal charge of +1, you would subtract an electron from your hybridization in your valence bond model. But what this does, it comes from your book. It shows really nicely the shape, the octahedral of the hybridized here in purple in the center. That's the hybridized orbital. And so fluorine is actually, because fluorine is has a single electron in an unhybridized p orbital here, right? So fluorine has a single electron, and so once they're all paired up, once the bonding occurs, all of these are paired up. So what you really want to do is you want to look at the hybridization before the sigma bonds or pi bonds, whatever is about to be made, are put in. Okay, so yes, so you can clearly see that's one of the f orbitals here. That sorry, f orbitals. Of f fluorine atom, it's a p orbital, right? It's a p naught, so it's a p orbital. One of the px, py, or pz. All right, so let's take that one step further. What if I ask you to come up with the valence bond model of C2H4? Step 1, you draw it. So you put carbon in, carbon, make a double bond. This one may take you a little while to figure out, but carbon has 4 valence electrons, so that's a total of 8 plus 4 is 12. So, and then we have 4 hydrogens, so 1, 2, 3, 4. So we have 1, 2, 3, 4, 5 bonds, and we have that's 10 electrons. We have 2 more. I just put them generically on 1 carbon, and so that shows you right away that this is deficient, so you have to make a double bond. Okay, so this has a double bond, and so the hybridization for just looking at one of these carbons, it has 3 regions here, right? 1, 2. The double bond doesn't mean there are 2 regions. There's just 1 region. We do distinguish between the double bond and the single bond, right? So this actually has 2 components. It has a sigma component, which is a direct overlap, and then there's a pi component. Now I'll show you how that works in a minute. But as far as the central atom is concerned, it has 3 regions, so it's sp2, right? So 1, 2, 3. We have an sp2. We have 3 sigma bonds, 2 to hydrogen, 1 to carbon, so single electrons here. And we happen to have a p orbital that is not used. And because the ground state is 2s, 2, and then 2p2, that means we have 4 electrons, and that 4th electron goes into an unhybridized p orbital. Okay, that's the one that makes that pi bond. Right? So these are sigma bonds, and that's a pi bond. Now I have some really nice pictures of that, but I'll try to draw it anyway. So we have a carbon here that has an sp2 hybridized trigonal planar center. So you make a sigma bond, you know, like this. And then what you have is you have an unhybridized p orbital here. That's a p orbital. And you got another one on the other carbon here, right? So you have another carbon that's also sp. So here's your hydrogen. And I really should just go to the picture. It's beautiful. But so you have these unhybridized pi bonds, and they're going to overlap above. And so you really have an electron cloud above and below, right? But we just draw it as a double bond. So now you can't really tell apart which one is the sigma and which one is the pi component. But valence bond theory tells you that you have two components, that every double bond has a sigma and a pi component. And so this would be I have a cleaner one here on the next, right? So here's the structure that we've drawn. Here's the ground state, and again I'm including the 1s. And so here we have sp2 hybridization. Those are the sigma bonds, and one makes a pi bond, right? Okay, so here's a definition. I've mentioned it more than once, but I finally have it in writing here. Sigma bond is a head-to-head overlap of two orbitals, and that you know, whether they're spherical or they just have direct, they have same energy and they have direct overlap, and so one electron from each. And a pi bond is a side-to-side overlap, so not direct. This is what it looks like. Okay, so here we have the molecule we just looked at, C2, and I'll draw it in the middle. So you kind of see it, and I'll try to draw it like this. And so both of those orbitals are shown here, right? The sigma component and the pi component is shown separately here, right? So in green here is the sigma component. Every carbon has three sigma bonds here, right? sp2, right? So shown here. Same with this carbon, right? And then this is what the pi component looks like. So you get an electron cloud above and below. Okay, that's going to become important when you study organic chemistry. Maybe that's in the fall, or I don't know, maybe. Here's another picture from the book. It looks a little different, but it's essentially the same. It shows you two p orbitals that are not facing each other, and they each have a single electron in there, right? So they can't flip, and there's already a sigma component here, right? So you know, so if there's already a sigma component here between, this is a direct orientation of two p orbitals with an electron, they can do that. They can make a sigma bond. But if they are side to side, they're gonna overlap like that, and they're gonna have this distorted looking electron cloud. All right. So I find that very fascinating. This is another example here of a pi and a sigma bond. If I draw this molecule out here on the side so you can see it. All right. So this is a carbon that's bound to an oxygen, and okay, so what they're showing here is, let's focus on the carbon. So the carbon, once again in purple here, that's your sp2 hybridization. Alright, so this has three sigma bonds, and it's sp2. But it also has a pi bond, and that's what you see here in red. Okay, oxygen makes, according to this scheme here, oxygen makes makes a sigma bond with one of the p orbitals, right? And then it has two more p orbitals, and it makes a side-to-side overlap. Okay? Okay. It also has two, you know, technically what oxygen does here, since it engages in bonding, it has three regions of electron density. It's worth looking at that, right? So it has 1, 2, and 3 regions. So it's also sp2 hybridized. And so you have 1, 2, 3. It's sp2. It has one sigma bond and it has 2 lone pairs in the other 2, right? So it has 2 lone pairs and it only makes 1 sigma bond. And then it still has that unhybridized p orbital. And that's where the pi bond is, right? So you have 1, 2, 3, 4, 5, 6 electrons, which is what you expect for oxygen. But the focus here is really on this carbon and having the sigma as well as the pi overlap. And it shows that here nicely. And this is from your book. Your book has some really nice pictures. Now let's take this one step further. Now we're going to make a triple bond. This is C2H2, which you now have a triple bond. And so looking at a single carbon, we have 2 regions of electron density, so we just need 2 orbitals. So this is linear, so it's sp hybridized, right? So here we have sp, and with a single electron in there. That means we have 2 p orbitals that are unhybridized with an electron each. Okay? The ground state looks the same. It's 2s and 2p. 4 electrons total, right? And so here are your sigma bonds and here are your pi bonds. So if I can draw that out, there's a picture that's better than what I can draw. But you take this one step further, right? So you have a linear component. So this here, looking at this carbon, we have sp, 2 regions, 2 sigma bonds. And then we have a p orbital that's here. And we have a p orbital that's here, right? pxy. And so we have the same thing here on this carbon. So we get that top to bottom pi component and then side to side pi component, right? So you have to envision that in 3 dimensions. There's a great picture here in a second. This is just the same thing we just did. And you should be able to label and identify which one of these is sigma, which one of these is pi. Okay, and this is what it looks like. It almost looks like some artist, some circus clown with these skinny balloons can make that. Anyway, right, so this is acetylene here, carbon triple bond, and like I said, one of these p orbitals goes up and down and one of them is left to right, and that's what you see here. So you've got this, the sigma bond is completely surrounded by electron density. And remember that this is going to pull it in closer. It's going to make the carbon-carbon bond distance shorter and also strengthen the bond, right? So you've got all these electronic forces holding this together, right? All right, so be able to do that. Distinguish between pi and sigma components for just about everything that I can throw in your ballpark, right? So let's practice 3 more and then move on to MO theory. Okay, so if I ask you to put on paper the valence bond model for BRF3, the first thing you need to do is draw the Lewis structure. You put bromine in the center. You have 3 sigma bonds to fluorine. They each have a lone pair, and I'm going to leave them off. And then bromine actually needs, in order to get to its 7, it needs 2 lone pairs, right? Because I didn't count valence electrons, I just went for formal charges. And I know that if I put 6 electrons on fluorine, I have a formal charge of 0, right? And since bromine is also 7, and I have 3 from the bonds, I need 4 more. So I just took 4 electrons and I put them on the center. So now you look what's around it. We have 1, 2, 3, 4, 5 regions. That means this is sp3, that's 4, right? D hybridization, right? So we have 1, 2, 3, 4, 5 regions. sp3d. So I had to borrow the 4d, empty 4d orbitals to make those bonds, and so I'm only using 1, so I need to also show the other 5 here. I'm going to run out of 4 here. 1, 2, 3, and 4. I'm going to run out of space, maybe not. And so this is the excited state. I haven't put in any electrons yet, but I can, because I know I have two lone pairs here, so I need 4 electrons that are paired up in the hybridized orbital, and I have 3 sigma bonds, so I need 3 single electrons in a hybridized orbital, right? So here we go, sigma, and these are the lone pairs. Okay, great. And in the ground state, you just go look it up. Bromine is so it has 4s, 4s2, and 4p5. 1, 2, 3, 4, 5. And those are the 7 electrons that are right here. 1, 2, 3, 4, 5, 6, 7 electrons. So this would be the example of BR, ground state. And I'm just, okay, ground state. And what you really want to do is you want to put the 4p orbitals in there as well. 2, 3, 4, 5, 4p. The 3, not p, it's d. Right, d orbitals, right? That's where we have 5. Not the 3d. The 3d are full and they cannot be used for that. Okay, let's work one more. AsCl5. Draw the Lewis structure. 5 bonds to chlorine. Arsenic's in group 5, so it's good with a formal charge of 0 in each of these chlorines, having 6 lone pair electrons. Also produces, I know they look like pigtails, they're supposed to be chlorines. Anyway, so you can also start with the ground state. You look up arsenic, and arsenic is in period 4 as well. So we have 4s, and there are 2, and then 4p, where are 3 of them, and then there are 1, 2, 3 electrons there. And then we're going to need the p's. So 1, 2, 3, 4, 5. D's. Why do I keep saying p's? Alright, so it's the 4 D's, and there are no electrons in it. And so here we have 5 regions, so it's going to have a sp3d hybridization, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5 electrons. These 5 electrons come over here, and they make 5 sigma bonds, right? And that's that. One last one, and then we'll take a break. Well, almost. We'll have a summary slide, and then we'll take a break, and then we move on to molecular orbital theory. Okay, now ClF4 has a plus charge. So watch what happens when you draw it. You draw the chlorine. You put 1, 2, 3, 4 bonds. Fluorine, 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 fluorine. I'm going to do it thoroughly. So we're going to put 6 electrons, valence of 0. Formal charge. Formal charge 0. Alright, 0. 1, 2, 3, 4, 5, 6, 0. Now if I do that for chlorine, chlorine is 7, and remember we got to come up with an overall plus charge. Minus the 4, 1, 2, 3, 4, right, is equal to 3, and so I need a lone pair here. And if I put that lone pair there, I subtract the 2, I still end up with 1, which is good. But that also means I have a plus 1 formal charge on the central atom. Therefore, my electronic ground state configuration is going to have 1 electron less than regular chlorine because of the plus charge. 1 electron has been removed in this case. So it's 3s, 2, and 3p, 4. Oofta. Look at this crap. Right? Instead of 5, it has 4, and that's because of that plus charge, right? And only this way is it going to make sense. And then we have 5 regions here, 1 and 3 sigma and a lone pair. So we're going to need the d orbitals. 1, 2, 3, 4, 5. I said d orbitals. Good for you. 3d empty, right? My hybridization is going to be sp3d. 1, 2, 3, 4, 5. I have a lone pair and 4 sigma bonds. 1, 2, 3, 4. Sigma, lone pair, and I don't have a pi bond here. but I will draw these anyway. They are empty. Those are the 3D. All right. So this is just a summary of what the shapes look like, and the electronic shapes and the hybridizations. Two regions linear, SP, SP2, SP3, SP3D, SP3D2 octahedral, right? And it indicates the approximate bond angles here. Of course, it depends. You know that you could have NH3, for example, which now this is pressing down, so the angle is no longer 109.5. But regardless, you have three regions here, so it has to be sp3 hybridized, and then we distinguish between the different kinds of molecules. Okay, so when we come back, we're going to look at the problems we have with valence bond theory. It doesn't say anything about paramagnetism, right? That's a problem. It also looks at a central atom, and but when you come back, I'll start here and we'll have a blast. Take care.